Alright, here's a second example of using substitution with definite integrals when you have upper and lower limits that you need to think about. Now this particular one's one we've actually looked at before and seen a couple different ways to do. The simplest way to do this one is to choose to use u as tan x here. And the reason being is because then you have its derivative right here, secant squared x dx, that you can make into du. Alright, so if you make u tan x, then du is going to be secant squared x dx. Alright, so we can change this to this equivalent integral here of u du. Alright, where that turned into that, and that turned into that. But the key here with this being a definite integral is changing those upper and lower limits of integration so that this remains equivalent to this, right? Both of them are just going to be a value, and they're going to be the same value. We have to track that. All right, so let's look at what we have here. We have u at 0, right, to figure out what the u value is at 0. So in other words, we need tangent of 0, which is actually 0. And we need u of pi over 4, or in other words, tangent of pi over 4. We're just subbing it into this, right? We created this. We decided that u was going to be tan x. All we need to do is tan of 0 and tan of pi over 4. Tan of pi over 4 is 1. So this is the same as saying the integral from 0 to 1 of u du, which is actually pretty easy to figure out here, because it's just going to be, if we're doing it analytically here, a half u squared is an antiderivative of u, and we can work it out for those two values. Alright, so we have a half minus 0, or in other words, a half. Alright, that's our value for that definite integral. This being a lot easier to work out than this analytically. Now we're going to have a quick look again here at what this looks like graphically. Alright, so let's graph those two functions and see what we have here. We'll call the first one f of x. That was tan x times secant x squared. And our second graph was, let's call it g of x, was just y equals x. Now again, I got to use x for this graphing software instead of u, right? Even though if we go back to our thing here, our first function was tan x secant squared x, and our second function was just u, right? So when we're graphing it here, we have to just put x for that. Boom, it's just that straight line. Now we're going to have to zoom in quite a bit on this, because all we're doing is looking at the area underneath this thing from more or less 0 to pi over 4, which is somewhere in this neighborhood here, 0.7 or 0.8, and 0 to 1 of the other one. We want to look at these two integrals here. Integral of f from 0 to pi over 4. We're going to have to go over here and get the pi that way. Pi over 4. Might take it a second. There we go. There's that area. 0.5 is that area, what we expected it to be. And then our second one, integral of g from 0 to 1. Now, again, that's a different area here that we're looking at under a different graph, under a different curve, but the areas are the same, right? You have 0.5 for each of those things. And it also really shows visually why you have to change those boundaries. When you change the function that you're using to evaluate your integral, you have to change your upper and lower limits of integration, all right, to maintain that same value, same area. All right, so that's using substitution with definite integrals, and the key again being, got to change those boundaries when you make that substitution. Not just 0 to pi over 4. When you write that integral, you got to rewrite it with new boundaries there. All right.